So I'm very pleased to be again in this inspiring meeting. And today I would like to share with you our results on the effect of infrared light on protein structural dynamics and protein interactions. For proteins to be biologically active, they need to undergo they need to be flexible, okay? They need to undergo so-called functional motions. And there are many studies linking those functional motions with water of hydration. And in the first slide, I would like to just show you two examples of such studies. So in one of those studies, it was shown that in order for the protein to be active, the water of hydration needs to undergo translational motion along the protein surface. So at low temperature, when only water vibration can take place, protein is immobile and inactive. Now when we increase the temperature so that the water molecules can slide along the protein surface, they're not fixed at the surface, okay, they can move along the surface, and only at this stage the protein becomes mobile and active. So for the protein motion, the water motion is necessary. And then there is another study performed in a group of Professor Gerard Pollack on the protein-based system, namely on the muscles. And in this study it was shown that on going from the relaxed to the activated state, there is a change in the water structuring. So in the relaxed state, we have these nicely ordered water molecules. This is hydrogen-bonded water, polarized, ordered by those proteins. And then when we go to the active state, we lose this water ordering, okay? We lose this hydrogen bonding. And this is reversible process. So we go back to relaxed state and we have again these ordered water molecules. So again, for the motion of this protein-based system, the water motion is necessary. And more than that, it has been shown also that this water, the structuring, is linked with partial loss of the protein structure. And there was a shift from the alpha helical structures to more beta sheet structures. So we know that protein motions are linked with water motions. So now, where's the place for infrared in it? And again, I also had the clue from the studies performed in the group of Professor Pollack, which showed that the infrared light is one of the most effective in inducing the structuring of the interfacial water. So at this slide you can see the increase in the volume of the structured interfacial layer in response to the beam of the infrared light. And then I performed myself experiments in order to show that this interfacial water structuring takes place also at the protein surfaces. So this is the image showing you the infrared spectra of lysozyme dissolved in water. And this part of the spectra, this band, corresponds to the OH vibrations coming from the water forming hydrogen bonds. And in general, increasing the intensity of this band is interpreted as increase in strength and cooperativity of hydrogen bonds. So you can see here that the effect of infrared light, this is this upper trace, is comparable to the effect of lowering our protein solution temperature. T0 means simply protein stored in ice. So what happens when we lower the temperature? Of course, the water forms more hydrogen bonds, it gets more structured. And the same happens at about room temperature, but in response to the infrared light. So we call it infrared-induced cooling of protein interfacial water, because the structural effect is like cooling, and it's kind of interesting observation because we all know that infrared light is a source of heat by itself. And we can also compare our effect of infrared light to the effect of placing our protein in a buffer solution with pH far away from its isoelectric point. So this again is infrared spectra of aqueous lysozyme. The bottom spectra is simply lysozyme in water. Now the upper spectra is the lysozyme in a buffer of pH 4.5. And now the spectra in the middle is the protein exposed to infrared light, but dissolved in water only. So again, you see that the effect of infrared light is comparable to the buffering, and what we do, if we place protein in a buffer, the protein gets charged. If it gets charged, it interacts stronger with water dipoles, so it induces this interfacial water structuring. And what we know more about infrared light, or more general about weak electromagnetic radiations. So there are many studies, experimental studies, which show that prolonged exposure of aqueous solution to the electromagnetic radiation, weak electromagnetic radiation, results in many effects such as increased conductivity of water, increased activity of ions, or increased surface tension of water. And I came across a series of works of Professor Shatao, who explained that all those phenomena can be understood if we consider presence of nanobubbles in aqueous solutions. And nanobubbles, in order to be stable, they are covered with ions. And because of this ionic covering, they can get polarized in electromagnetic field, and this induces bubble movement. It induces bubble to surface interaction, and at the end of the day, after prolonged exposure, it makes the bubble to coalesce, grow, and escape from solution. So the effect is like degassing. So if those bubbles leave the solution, the effect is increased conductivity of water, because the water that was immobilized in the bubble surface is now free to move in electric field. The same is true for increased activity of ions. Now the interfacial tension can increase because when the bubbles leave the water has more opportunities to form the hydrogen bonds with other water molecules. But in the light of what we know about the effect of radiations, electromagnetic radiation in water, it can also act the other way around. It might be that electromagnetic radiation in fact induces water structuring, and this structuring exposes bubbles, nanobubbles, and therefore we have these effects. But it was also shown that if people apply electromagnetic radiation to degassed water, there's no effect. Anyhow, because all bioliquids contain some amount of gas, and part of this gas will be present as nanobubbles, then if we think about the effect of electromagnetic radiation on biological samples, we should also take into account the nanobubbles. So this is kind of the motivation and the context in which I will discuss now our new results. So what we did, we simply exposed our proteins in aqueous solution to the infrared light for the maximum exposure time of about 10 minutes. And we used as a source of infrared light-emitting diode with the maximum emission at 2.9 micrometers, and all this emission spectra corresponds to the region in which liquid water strongly absorbs infrared light. Then the optical power of our light source can reach to 30 microwatts, and for comparison, the optical power of sunlight at the sea level is about 1,000 watts per square meter. So this is really weak electromagnetic radiation. And as a first step, we wanted to see how this weak electromagnetic radiation, this infrared light, affects the protein secondary structure in solution. So to do so, we performed the Fourier transformed infrared spectroscopy measurements on our proteins. So here I would like to show an example. I would like to stress that this is the example because we have seen similar behavior also for other proteins. This is Bowen serum. This is the secondary derivative of infrared spectra for Bowen serum albumin, dissolved in imidazole buffer. And you can see here the significant contribution of the random coil structure. And this makes sense because those imidazoles that are present in our buffer, these are surface active species, in a sense that they attach to the protein surface as they interact with hydrophobic surfaces, but they also are hydrated, so they pull those surfaces, so those hydrophobic compartments to water. They can partially denaturate protein, and then they also form hydrogen bonds with many other protein compartments, and they can compete with native hydrogen bonding. And we have been storing our solutions in the fridge, what is normal for storing your protein solutions, and it's also known that low temperature denaturation process is assisted. So, but now, look, we take such solution, we equilibrate it to room temperature, and now we switch on our infrared light. And just look what happens. So the random coil structure decreases, and we increase the contribution of the alpha helical structure. Then we go again back to the more disordered conformation, and then back again to the more folded structure. And by using infrared light in pulses, we could go back and forth with such structural fluctuations between those partially disordered and more folded conformation. And here I'd like to show you already. Yes, I'm sorry, I was told that I have to fit in time. Okay, so I will try to talk more slowly. So here I would like to show you already the Fourier deconvoluted and the fitted spectra of our bone serum album indissolved and indissolved buffer in those two extreme substates. So this partially disordered state with great contribution of the random coil and this more folded conformation. And now this folded conformation resembles very much conformation of our protein when it's dissolved in water only. So when there are no those surface active and structure distorting ions. Now this disordered conformation is characteristic for our protein in the presence of those surface active ions and for the solution that has been stored cold, because as I said, it supports aids denaturation. And it's also characteristic for the solution that has been degassed. Now, our protein can be found fold in solutions when there are no surface active ions, like in water only, here, or in solutions when we have gas cavities present. So how do we know gas cavities or nanobubbles? So how do we know that there are gas cavities? How do we create them? So we take our solution that was stored cold, we take it out from the fridge. This is in this partially disordered conformation, and we bring it quickly to about 36 degrees. And by doing this sharp temperature gradient, we sharply diminish the solubility of gas in solution. And this is the known method to induce the nanobubbles in solution. And by doing this sharp temperature gradient, we can induce the structural transformation from this disordered to more ordered conformation without the use of infrared. Okay, and then if we simply slowly equilibrate our sample from the cold state to the higher temperature, then there is no structural change because we have no mechanism for the bubble nucleation. And then we try also to go the other way around. So we take our protein, which is folded in solution, and then we degas it by the vacuum pumping. And by doing so, we induce transformation from ordered to disordered conformation. So it implies that, in fact, the nanobubbles, they are involved in the protein folding. And now, if we apply the infrared to the degas solutions, we observed no effect of infrared. So it suggests that nanobubbles, they mediate the observed by us effect of infrared on our proteins. So on this slide, this is absolutely out of scale. This is to show you the concept, how we understand the problem, what we think is going on. So we start from this partially distorted conformation with those circles here indicating those surface active ions. They attach the surface and they pull it toward the solution. They partially denaturate it. And then we apply our infrared light. And if you remember from the beginning, infrared light, it induces the bubble movement in solution. So if there are any nanobubbles, they tend to stick to the surfaces. They tend to also stick to protein hydrophobic compartments. And by doing so, they displace those surface-attached ions. And what those ions were doing here, they were providing additional protein-water affinity. So they were decreasing the protein-water interfacial tension. They were providing additional solubility to the protein. Now when we have the nanobubble here, we increase the surface tension, and it induces the protein fold. And infrared light, because it has this heating effect, now our proteins our solutions are thermostated. The temperatures of a whole system is stable, but nevertheless there are no local heating effects. And because of them, we can even probably have the nucleation of the bubbles, because we can very locally reduce the solubility of gas to our sample. Now, if we continue irradiation for a long enough time, then we can induce the bubbles along the surface, and generally we increase the temperature to Mars, so they meet each other, they coalesce, grow, and they can escape, and then we will have this backward transformation. And that the nanobubbles are in fact involved in the protein folding, there are other studies suggesting it. There are theoretical studies suggesting that nanobubbles in fact are the factor that drive primary protein fold on the moment of protein synthesis. So that gas cavities are formed in those hydrophobic compartments, and because they are covered by polarized water sheets, they act as attractive resonators. They attract each other, and they attract also those, by doing so, they attract the hydrophobic compartments to each other. And then there are many studies showing that nanobubbles are in fact responsible for so-called long-range hydrophobic interactions in solution. So if there's a nanobubble in between of the hydrophobic surfaces, it creates capillary force, and they sense each other from quite large distance, and they come to each other. So, because as I said at the beginning, in order to be active, protein needs to be mobile, protein needs to be flexible. It might be that because these nanobubbles are involved in the protein fluctuations, that might be involved in the native protein functioning. It is interesting in this point to look at the studies. These are not my studies. They were looking at the probability of bubble nucleation depending on the solution temperature. It was a very interesting observation that there was clear onset of the bubble nucleation at about 34 degrees, and then around 50 degrees there is no bubbles anymore. So there is a window of nanobubble nucleation that corresponds roughly to the physiological temperatures. So it can suggest, again, the link between the native protein functioning and the nanobubbles. And then also the results of our study remind me very much the concept of Gilbert ring of the cell bioenergetics functioning because of the protein transition between the resting and active state. So in this concept, we have those protein in resting state, this with extended polypeptide chain, and that polarizes water molecules, so we have here low entropy and high energy state. And then when protein folds, this interfacial water structuring lost, so we have gain in entropy, and this entropy can be used to perform biological work. And now if you look at the results of our experiments, so we also have transition between this partially disordered and more extended conformation, which is also more hydrated conformation, and this folded, more compact conformation, which is less hydrated because on creating fold we also lose some water of hydration. In my images, those circles indicate not water but ions, but those ions bound to the hydrophobic compartments provide the additional protein-water affinity. And yet another process for which our findings can have some implication is that of heat and cold protein denaturation. So we know that the proteins are nicely folded at about physiological temperatures, but then when we cool down the solution and when we heat the solution, they denaturate. So if we think about cold denaturation, this is the exothermic process, and this is usually reversible. And this is commonly accepted that the driving force for it is the formation of hydrophobic cages around the nonpolar compartments that are now exposed to the solvent. So the enthalpy gain comes from those hydrogen bonds formed between water molecules. Now if we think about our experiments, what we do is we cool down our solution, so we increase solubility of gas in solution. So we dissolve nanobubbles. If the gas dissolves in water, it forms bonds with water, so this is an exothermic process. We have enthalpy gain. And now why the process is, and we lose the protein structure because, as I was trying to show, nanobubbles are involved in the protein fold. Okay. And why the process is reversible, because when we now heat our solution, we have this gas stored in it. So we can again nucleate nanobubbles, okay? And we can again make our protein to fold. But if we think about heat denaturation, now this is an endothermic process, and it is very often irreversible. And again, this is commonly accepted that the driving force for it is the entropy gain coming from those nonpolar compartments that are now more free to move in solution. If we think in terms of what I've observed, so what we do when we increase the temperature, with the diminished solubility of gas, it escapes from the solution. Okay, so again, if there are no nanobubbles, there is no protein structuring. But now, if we cool down the solution, and with the nanobubbles escape, then we have increased water activity. We have entropy gain. And when we cool down the solution, we have no gas stored in it, so we do not form bubbles anymore. So this is an irreversible process. And now I would just show you some calculations done by Professor Shataov regarding the bubble motions in solution, because what was often observed that there are so-called after effects of exposure to electromagnetic radiation. So even after we switch off the source of radiation, the effects are still observed and they often oscillate. So this is simply some coefficient of wave function versus time. It shows some pattern that repeats itself on different time scales, and it represents some bubble properties and simply means that those bubbles, when they are present, they fluctuate, they naturally fluctuate. So they are nucleated, they join to escape, and they are born again. And because there are bubbles naturally present in biological systems, and because they might be involved in protein fluctuations, so we decided to look if those fluctuations can help protein to function. So we performed very preliminary results on the lysozyme enzymatic activity in controlled conditions and in response to infrared light. So this is red-green trace represent control conditions. Now this pink trace represents the kinetic of the reactions after exposure to infrared light. So you can see here simply decreasing absorption of the cells in response to the lysozyme activity versus time. So you can see that the kinetics of the reaction increases after exposure to infrared light, which may indicate that those infrared-induced bubbles fluctuations and protein fluctuations can support protein functioning. And here is for comparison the kinetics of the reaction in the gas solution. It's much slower, so it again implies that in fact those nanobubbles are involved. And all those results about the protein structure in response to the infrared light, they were done with the use of infrared spectroscopy. And just to be sure that this is not some artifact coming from the technique itself, we also performed just cross-check experiment and used UV-Vis spectroscopy. And this is again spectra of bone serum albumin at control conditions and after exposure to the infrared light. And we see here decrease in the absorption in 278 nanometers. And this decrease in absorption is interpreted for bone serum albumin as increase in folding, because some of the tryptophans that absorb here are now hidden in the structure, so they do not absorb light effectively. So we also wanted to look at some protein interactions that can be affected by infrared light. And we were investigating protein surface interactions. So we have been adsorbing our proteins in the surface of nanoparticles. We selected silicon nanoparticles and proteins lysozyme of albumin and bone serum albumin in different media, water, salt, and a buffer. And this is the graph that summarizes the results. You have been then, sorry. We have been measuring changes in hydrophilicity of those protein-coated nanoparticles in response to infrared light. So on this graph, those positive changes mean that the proteins coating nanoparticles get more hydrophilic after exposure to infrared light. Now, negative changes means that they, in fact, get more hydrophobic. And I would like to start from the second case, because I was talking about BSA in imidazole, and this is exactly this case. So how we can understand it? So we can think about those transitions that I was talking about. So we start from our protein, from our solution in which protein is partially denaturated. It was cold storage solution, and then we apply infrared light. We have this folding. Okay, so we lose those surface bond ions that were providing additional protein water affinity, and we end up with more hydrophobic protein. And we also have some indirect evidence coming from complementary technique from quartz crystal microbalance, confirming that indeed after exposure to infrared light, those proteins have less water affinity. So what we can see with quartz crystal microbalance is the adsorption of protein on the quartz sensor, and here the decrease in the frequency is proportional to the adsorbed mass. So this is the control conditions, the gray trace, and this trace is after irradiation. So after irradiation, we have much more mass of protein adsorbed what can indicate that it has, again, it has in fact the less affinity to the water and more propensity to the solid surface. But this is not the only effect of infrared light on the protein surface interaction, because even more important is the fact that we observe that infrared light protects our protein from denaturation on adsorption to the surface. So this is again the second derivative of infrared spectra. This is for BSI again, but it was also the same for lysosome or for oval booming. So this is in control conditions. We can see that it partially denaturates on adsorption, and this is after irradiation. So we preserve the folded conformation. And this is very important because when protein is folded conformation, we know that it can preserve its functions. And we think that the reason for this is this other effect of infrared light, namely the water structuring effect. When we induce this structured water shell, we kind of protect our protein from denaturation. And this is, I think, also I think this is also the reason why for other proteins or for BSI at other conditions without the presence of those structure distorting ions, after the irradiation, hydrophilicity of our proteins in fact increases. So we can understand it by taking into account this water structuring effect of infrared. And again, we have indirect effect, confirmation coming from quartz crystal microbalance. This time, the amount of proteins adsorbed after irradiation is less than without irradiation, which suggests that in fact protein has more water, more affinity into the water after irradiation. And if we look at the first stages of the adsorption of lysosome and the quartz surface, there are control conditions. So we start depositing our proteins, it adsorbs, it reaches some plateau, and this is dissipation energy indicating softness of the system. And if we now look at the irradiated protein, we see very substantial difference. So there are very characteristic spikes in the adsorbed mass and dissipation energy, and they are interpreted as adsorption of something what was highly hydrated, and it simply loses some water of hydration on adsorption of the surface. So it indicates that in fact this protein hold more water after irradiation. And it was also interesting for us to understand why we see the differences in those water structuring properties for different proteins. And we observed that it correlates quite well with the presence of so-called basic functional groups at the protein surfaces. So those basic groups, these are those that have partial negative charge, and they like to become protonated, become positively charged. And there are other studies confirming, in fact, that those positively charged amino acid residues are those that form the strongest and the longest-lived hydrogen bonds with water. So if we look at the results, this is a table that shows the amount of those hydrophilic and basic functional groups in different proteins. So in our BSA and lysosome, the amount is quite the same. If you see the water structuring effect in water only, it's quite similar, unlike in the case of oval booming, which has less those groups and it has less structuring effect. And now just very quickly, I would like to show you that we have also been using infrared light to affect protein crystallization. So we prepared protein crystallization droplets in which we reduced the protein concentration up to the point that there was no nucleation at all. And we exposed such drops to infrared light. We observed beautiful crystal nucleation, and these were diffracting crystals. So again, we think that this can be explained by this water structuring effect of infrared, because it is known from protein studies that the main driving force for the protein crystallization, I'm out of time? 1 minute, okay. Is the entropy gain on releasing water of hydration when protein contacts are formed. So if we increase the structure of the hydration shell, then we increase the entropy gain on this contact formation, so we can have this nucleating power. And even more interesting than that, if we change the conditions so that we formed jelly precipitate instead of crystals, and it simply means that this is non-specific aggregation, interactions went too fast. And if we applied infrared light to such conditions, we formed beautiful crystals. So it means we prevented non-specific aggregation. It can be due to this structured wattle layer that allows the protein to rotate to find orientation before they form contacts, or it can be because of those fluctuations. So we increase the probability of the protein to be in this folded state, so to form the proper contacts. So now we go to conclusions. We're able to show that infrared light can induce the protein structural fluctuations between this partially disordered and more folded conformation. We also think that the nanobubbles really mediated those protein fluctuations. And a very important observation, infrared light, it prevents the protein denaturation on adsorption on the surface and also prevents the non-specific aggregation solution. And non-specific aggregation is, that you may know, involved in many diseases. So thank you very much for your attention.